In 1958, the New York Times released this article. Dr. Frank Rosenblatt, who is an American psychologist and considered a pioneer of deep learning, had just made his most recent discovery. The article considered it the embryo of an electronic computer that the Navy expects will be able to walk, talk, see, write, reproduce itself, and be conscious of its existence. We'll first need to define a feature vector. We'll call it x. X is d-dimensional, meaning the number of elements, or in this case features within x, is denoted by d. These are features. You can think of each one of them as describing x. It's also common practice in machine learning to transpose the vector x. You can think of x as a sample that lies within our dataset, which has many x's. Now, I know, when I was first presented with all of this notation and information, I was quite confused, so if you don't quite get it at first, I encourage you to pause the video and take some time to think about it. For now though, we'll define each of our labels with y. Y is going to be positive or negative, and each x has its own corresponding y. So that is, the piece of data is going to either result in a positive or negative value. We can then accumulate all of this data into a fine notation denoting the set of samples we have. We can then define our domains for x and y. We can set n equal to 10, so we have 10 samples, and the dimensionality of d equal to 2. So we can plot our 10 samples on a 2D plane. This is because all of our x feature vectors have only 2 features in them. So our axes are x sub 1 and x sub 2. Now, more notation incoming, but we're going to define our ith prediction, in this case we're going to call it y hat, equal to the sign of the dot product between the ith feature vector and our theta vector. Sign just figures out whether the value within it is positive or negative. Okay, but what is this theta vector? We'll define it like this. We can first note that it is the same dimension as our x vector, d-dimensional, and each theta sub 1, theta sub 2 to theta sub d are basically our weights. In this case, we have 2 weights. We're going to learn these weights with this algorithm here. This is the Perceptron algorithm. In this first line of our pseudocode, we set all of our weights to be equal to 0. We'll then perform the body within this while loop until we have correctly classified all of the points within our dataset. That is, all of our predicted labels match those of the true labels. For every iteration through our while loop, we iterate through all of the points within our dataset. So from I equals 1 to n, where n is the size of our dataset. This next line of code is basically checking whether the given true label associated with the ith piece of data matches that of our predicted label for that piece of data. Remember, we find that predicted label by taking the dot product between our theta vector, or the vector of weights that we intend to learn, and the feature vector associated with the ith piece of data. It can be a little useful to get rid of that sign thing, so we can take this line of code and rewrite it like this. Here we're just taking our true label and multiplying it by that of our predicted label. If that's less than or equal to 0, then our prediction was wrong. We perform the following line of code. This is our update step. This is where we learn theta. If our prediction was wrong, then we take the ith piece of data's true label and feature vector, multiply them together, then add them to what theta currently is. And that's it. That's our pseudocode for the perceptron algorithm. But I think it's best to understand it through a visualization. We'll start by making this point in the center of our plane. This is just where we initialize our theta vector to be the 0 vector. We then check whether all of our points are correctly classified, and, well, none of them are. When you think about it, that if statement is basically checking this, where the dot product in there is always going to be 0, and 0 is less than or equal to 0. We then iterate through all n points within our dataset, starting at I equals 1, and we check whether or not this point is correctly classified by our current theta. We already discussed that it won't be, and here we can see that it's in fact not. So we move into the next line of code. We update theta. Now we set I equal to 2 and move to our next point. We can note that this point is also incorrectly classified by theta. So we once again update theta. We then set I equal to 3 and move on to our third point. This point is correctly classified by theta, so we don't perform an update step. To speed things up, we'll automate the rest of the points, seeing how each may or may not affect theta. So now our algorithm has correctly classified all of the points and is done. We can visualize this with a decision boundary, where all of the positive points are on that orange side and all of the negative points are on that blue side. And in our case, our theta has correctly classified all of our points, positive and negative. We can find this decision boundary through some nifty little algebra by taking the equation in our if statement, which asks whether or not our prediction was right or wrong, and setting it equal to 0. This is just the dot product between our theta vector and the feature vector. We can plot all of these points where this dot product is 0. We can also move this equation into slope form to get our decision boundary. Okay, so we just saw how the perceptron algorithm can learn to classify a set of data points, but these data points were linearly separable. What if they weren't linearly separable? Not just that, but what if they weren't even linearly separable through the origin? Well, let's look at this case and work through it. For this case, we'll just iterate automatically through every one of our points, using a decision boundary to visualize how our theta vector classifies these points. We can see that our theta vector has no issue updating and the algorithm seems to be working as normal. Except this time, after iterating through all of the points in our dataset, we will not have correctly classified all of them. And we can iterate through our dataset many more times and find that it will sort of end up oscillating between these two positive points. And we'll come to find that we can never actually correctly classify both of these positive points at the same time. And this is because even though our dataset is linearly separable, it's not linearly separable through the origin. So what we'd like is a way to push our theta vector off of that origin, away from it. So maybe we can correctly classify all of the points in a dataset like this one. To achieve this, we'll add an offset term b to our theta vector, which increases its dimensionality to 3. This in turn will also make all of our feature vectors have a dimensionality of 3, and we'll append them all with a 1. We can see why we append them with a 1 by finding the decision boundary again. Through putting it into this form, we can see how this new offset term b can allow us to push our decision boundary away from the origin if we need to. We'll run through our algorithm again, initializing the theta vector to be the 0 vector. Again, we see that our first point is incorrectly classified. And so we can perform the update step, where we'll see this offset term come into play. We'll then move on to our next point at I equals 1, and see that it is also misclassified as it ends up equaling 0 actually, and we'll perform the update step again. We will then, as before, iterate through the rest of the points automatically. We find that we don't correctly classify all of the points after the first iteration through our dataset, but after one more, we get this decision boundary, which correctly classifies all of our points. So there we go. We've seen how the perceptron algorithm can learn a set of weights to make predictions on the labels contained within a dataset. But this data was all linearly separable. What about in the common case where the data isn't linearly separable? Well, we'll see how other algorithms similar to this foundational perceptron algorithm are able to handle this with varying degrees of error.